and calculus for several real variables. In this lecture, we are going to talk about the Lagrange multiplier method for calculating maxima and minima. To what kind of problems we will make use of this technique, that is for constraint maxima and minima, we will make use of these techniques. So what do we mean by a constraint maxima and minima? And what is the necessary to make use of a Lagrange multiplier? Already we have some techniques through which we can calculate the maxima and minima value. But what does this need? Those things we will see in this lecture. Here, initially let us start with the problem to understand the instances where the Lagrange multiplier method is needed. Here we are asked to find out the point on this plane. So we are given with some plane and we'll have to find a point so that this point is closest to the origin. That is, you will have to find out the minimum value of the distance from origin. Okay, so the distance between any two points, is given by the formula x1 minus x2 whole squared plus y1 minus y2 whole squared plus z1 minus z2 whole squared, everything under root. So if we are talking about the distance from the origin to any point, and the point let us take it as xyz, and the origin is 0 0 0. That is, if you replace x1 is equal to x and x2 y2 z2 is 0, then the function that you have to consider here. Okay, let me write that function as d. Since it is distance, let me write this way. This is under root x squared plus y squared plus z squared. Okay, where can you take this point P? This point has to be taken from this plane, because you are going to find out a point on the plane which is very closest to the origin. So it is, you will have to find out the minimum value of this distance such that your xyz is on the plane 2x. Sorry, I think it is doing something wrong. So on this plane only you will have to take. Okay, so 2x plus y minus z minus 5 is equal to 0. That is the plane in which you will have to take the point. So proceeding further, whether you are finding the distance from this point to the plane, okay, anyway we are finding the distance, whether you consider the minimum value of this function or the squared one. So the squared one, let me take it as fyz. Let that be x squared plus y squared plus z squared. You may ask me, is it necessary to convert this to this function? Can I proceed with the under root x squared plus y squared plus z squared? Yes, of course you can proceed with under root x squared plus y squared plus z squared. But to make the calculations easier, we are converting this way. So here if you look at it, you may very well see it is a function of three variables, and you will have to find out the minimum value of this function subject to the constraint, that is 2x plus y minus z minus 5 equals 0. So from which you can deduce your z value as 2x plus y minus 5. If you substitute the value of z in f, this becomes some function of x and y alone, that is x squared plus y squared plus 2x plus y minus 5 whole squared, and it is okay. So you do not have this any subject to this condition, because you have plugged in the value of z from this condition only. Now you just have to find out the max, the rest of the things using this h only. So if you have this h and try to identify what is hx, that is del h upon del x, it is 2x plus 2 times of 2x plus y minus 5 multiplied with 2. So that is 2x plus 8x plus 4y minus 20, that is 10x plus 4y minus 20, and this has to be equated to 0. Okay, and if you find hy, it is del h upon del y and that is 2y plus 2 times of 2x plus y minus 5 multiplied with 1. Therefore, it is 2x plus 4x, sorry, 2y plus 4x plus 2y minus 10, that is 4x plus 4y minus 10 equals 0. Right? Now we will have to, we have equated these two things to 0. So this tells you your 10x plus 4y is 20 and 4x plus 4y is 10. If you subtract these two things, you get 6x is 10. So from which your x value is going to be 10 upon 6. That can also be written as 5 upon 3. If you substitute your x is equal to 5 upon 3 in any of these equations, so 4 times of, okay, let me write down, 4 times of 5 upon 3 plus 4y is 10. So 4y is 10 minus 20 upon 3, that is 30 minus 20 upon 3, that is 10 upon 3. So if you take your y value, it is 10 upon 3. So you get what? So it is 5 upon 6. You get your x value to be 5 upon 3 and y value to be 5 upon 6. Right? So the same, we have got these values, and with the help of second derivative test we shall show this is the minimum value, for which let me find out my okay, so these are to verify these things, let me do it in another color. So hxx, it is my hxx is going to be 10 and hyy is 4, hxy is 4. So 10 multiplied with 4 minus 4 squared, which is 40 minus 16, which is going to be 24, which is a positive quantity here. And my hxx is also positive. Therefore, the point that we found, that is 5 upon 3 comma 5 upon 6 is minima. That gives me the minimum value. So we verified that one, and here let us see what z is. Z is 2x plus y minus 5, and if you substitute the values of x and y into it, you get minus 5 upon 6. So the closest point on the plane to the origin is this one, and if you have to find out the distance, that is under root 5 squared upon 3 squared plus 5 squared upon 6 squared plus minus 5 squared upon 6 squared. So it is if you just multiply 2 squared on both sides, it's gonna be 10 squared. So 100 plus 25 plus 25 upon 36. So it is under root 150 upon 36. So you can cancel this with third table, and you see, I think you can cancel it with 6th table itself. It is going to be 6 and it is 25. So it is 5 upon under root 6. That value is approximately given as 2.04. This is the shortest distance from the origin to the plane, and the point at which the shortest distance occurs is this P. Here, this problem was quite easy, and that is why with the help of the previous methodology, that is with the help of previous idea itself, we were able to solve this problem. Now, let us see another problem. Okay. So here, we are asked to find the points on the hyperbolic cylinder. So that cylinder is given to be x squared minus z squared minus 1 is equal to 0. That is, if you see, so you will have to identify some hyperbola and you just extend it along y-axis. So that type of geometrical shape, we call it as the hyperbolic cylinder, and you will have to find the points on the cylinder which is closest to the origin. Okay, we may think that it is similar to the previous problem. Yes, of course it is similar. That is why we have considered the same function here too. From the given constraint, that is x square minus z square is equal to 1, from this we write z square is equal to x squared minus 1, and we plug this one into this f and convert the f into a function involving x and y. Okay, and if you apply your h6, that happens to be 4x, and hy is 2y, and if you equate them to 0, you are getting your xy to be 0 0. Okay, but we failed to notice one thing here. The cylinder is about the cylinder is x squared minus z squared is equal to 1. So the point 0 comma 0 does not lie on the cylinder. We will have to identify a point on the cylinder which is closest to the origin, but we have identified some point that is not on the cylinder. So what should we do? We will have to convert the function fxyz as a function of y and z. We have converted it to a function of x and y. So what shall we do? So from this one, we shall write x squared as z squared plus 1 and substitute in the given function, and you are going to get some other function that involves y and z. Okay, so if you put x squared is equal to z squared plus 1, it is going to be y squared plus 2z squared plus 1. So this is going to be your function. Okay, with this function, you can find out your ky and kz and equate them to 0. You get y is 0 and z is 0. If you give your z is 0 in this quantity, you get your x square is plus or minus 1. Therefore, you get the points 1 0 0 and minus 1 0 0, which are lying on the cylinder, which are lying on the hyperbolic cylinder, and that is going to be the closest distance from origin. So from the diagram itself, you may very well see that is happening. Okay, this is one way of proceeding. And the other way is, from the origin you consider some imaginary sphere. Okay, you try to what to say, you try to magnify the sphere so that the sphere just touches the cylinder. It is not intersecting the cylinder, it just touches the cylinder. You will have to identify such a sphere. So at the point of contact, the sphere as well as the cylinder will have a common tangent plane and the normal line. So with that idea, with that geometric ideologies, if you consider, we can derive what is called as Lagrange method. Okay, so the equation of the imaginary sphere that we considered is given by this one, and this is the hyperbolic cylinder that we have. Okay, here what are we saying? They'll have at the point of contact, they'll have the same tangent plane and the normal line. So we shall equate these two things. So from which, from your f, you find what is your del f upon del x, del f upon del y, and del f upon del z. And that happens to be 2x comma 2y comma 2z. So from here your del g is gonna be del g upon del x comma del g upon del y comma del g upon del z. So this is going to be 2x comma 0 comma minus 2z. So if you equate them in the vector notation, you get this quantity. Okay, so equating the corresponding coordinates, we get 2x is equal to 2 lambda x and 2y is 0 and 2z is equal to 2 lambda x. So from these quantities, you may conclude your y coordinate is 0. Now you will have to identify what is your x coordinate and z coordinate. Okay, so we will have to be very clear with the points that can lie on the surface, that is on the hyperbolic cylinder. Okay, so if my x quantity is not 0, okay, if my x quantity is not 0, then this very well tells me that my lambda has to be 1. Okay, so if I plug in my lambda value is 1, here I get 2z is minus 2z, and that forces z is 0. So we get the point what? Z is not 0, lambda is 1. So if you give okay, so you are going to get x comma 0 comma 0, right? So you just see here, you know z is 0, you have found z is 0, just plug in your so from using these calculation, you have found z is equal to 0, substitute z is equal to 0 in it, and you will get your x squared is 1. This gives you that your x can be plus or minus 1. Okay, so these are the closest points on the cylinder to the origin. So what we have used over here, okay, here we have used something, right? So these ideologies is called as the Lagrange multiplier. Now let us formally state what do we mean by a Lagrange multiplier ideology. Okay, before proceeding to it, we have an orthogonal gradient theorem. That is, if you have a function which is differentiable in some region whose interiors contain a smooth curve. That is, for a two variable case, I am telling you. Suppose if you have to consider for a three variable case, that is uh, your variable, your independent variable is a three variable, is a three-dimensional variable. Okay, if you have to plot your function value, that will be in the fourth dimension. So here you have some region. Okay, here you have some three-dimensional region. This contains some smooth curve. Smooth curve means everywhere differentiable. Okay, if you contain some smooth curve that is given in a parametric form. Okay, and if p naught is some point on this curve where your function has a local maximum or a local minimum, okay, then your del f is orthogonal to this curve at that point. So for which what do? We just take the gradient vector and see whether the dot product is 0 or not. So this is what is v? That is the points, the derivatives of the curve at that particular point. Okay, so the same ideology here, it is spoken for three variable case. The same ideology can be extended for two variable if needed for any number of variables, right? So the method of Lagrange multiplier, suppose you have a function, if you have two functions which are differentiable and the gradient of the second function is non-zero, okay, whenever the function is equated to 0, to find the local maximum or minimum values of the function subject to the constraint. So here the function f is the objective function. That is whether you will have to maximize or minimize, that is your function f. And this function g equated to 0 is constraint function. Based on this constraint, based on this restriction only, we will have to identify the maximum and minimum values. To do so, we will have to find the values of x, y, z and lambda which simultaneously satisfy these conditions. For a three variable case, what does it mean? It means your del f upon del x is lambda times of del f upon del g. Sorry, del g upon del x. And similarly, del f upon del x, sorry, del y is lambda times of del g upon del y, and your del f upon del z is lambda times of del g upon del z. Okay, here we have three equations and you have the fourth equation, that is your constraint. Okay, you will have to make use of these four equations to find out the value of x, y, z and lambda. Okay, sometimes it will happen that first we will find lambda and with the help of lambda only we will find all other values. Okay, that may be the case. If that is the case, of course we'll have to find out all these possible values, but to complete this problem the values of x, y, z is required. The same ideology can be extended for any number of variables. Okay, if you have to talk for two variable case, then what would you have? You will have only del f upon del x is lambda times of del g upon del x, and del f upon del y is going to be lambda times of del g upon del y, and your constraint equation will contain only two variables and that is equated to 0. So this may be the case, and for this problem actually using this only you are going to find out the value of x and y and the value of lambda to find the maximum or minimum, that is to optimize this function with respect to the constraint g of xy is 0. Okay, now let us get into the problems. Here in this problem we are asked to find out the greatest and smallest values that the function takes on this particular ellipse. Okay, we'll have to find out the extreme values of this function subject to the constraint. Okay, extreme value of the function what? That is xy. Subject to the constraint what? X square upon 8 plus y square upon 2 minus 1 equals 0. Now, to proceed further, what should we do? We'll have to find out these two quantities. Okay, I think you people can do it. My pointer is not working that good. Okay, yeah. So hopefully it works with the highlighter. Yeah. So this is the condition that you'll have. Okay. So from which what should you do? You will have to find your f of xy is what? Simply xy. So from which your del f upon del x is y and del f upon del y is x. Okay. Your del f upon del g is what? Sorry. Del g upon del x is what? It is 2x upon 8, that happens to be x upon 4, and del g upon del y is 2y upon 2, which happens to be y. So from this one, what you are going to have is y is equated to lambda times of x upon 4, and x is going to be equal to lambda times of y. Okay, these two are the equations. So if you plug in the value of x in the first equation, you are going to have your y is lambda squared upon 4 times of y. So this gives you your lambda square is 4, therefore your lambda value is plus or minus 2. Once you get your lambda value, give it to x. That is the relation between x and y. So you have your x is lambda y. Okay, therefore your x is what? Plus or minus 2y. Okay, fine. Now, let us consider the case when my y value is 0. If my y value is 0, that forces that x is also 0. But you can see very well that the point 0, comma 0 is not lying on the ellipse. So this cannot be the case. So when your y is non-zero, you get your x to be plus or minus y. And if you substitute that in the given equation, that is what? In your g. So that is x squared upon 8, right? So 2y, whether be it plus or minus the squared upon 8 plus y squared upon 2 and is equated to what? 1. So this is gonna be 4y squared upon 8 plus y squared upon 2 equals 1, and this is y squared upon 2 plus y squared upon 2 equals 1. Therefore it is y squared is 1. Therefore y is plus or minus 1. If your y is plus or minus 1, then your x is what? Plus or minus 2. Sorry. Yeah, right. X is plus or minus 2. So you are going to get these 6 possible values. Sorry, this 4 possible values. Okay, so at all these points you are going to get your extreme values. The extreme values can be either maximum or minimum, and the maximum value is 2 when you substitute both in positive or both in negative, and one positive one negative gives you xy is minus 2, that is the minimum value. Okay, similarly here you have a problem. We are asked to find out the maximum and minimum values of some function, that is 3x plus 4y, on this circle. So here your f of xy is what? 3x plus 4y, and your g of xy is x squared plus y squared minus 1 is 0. Your del f upon del x is 3, del f upon del y is 4, del g upon del x is 2x, and del g upon del y is 2y. And if you equate del f upon del x to lambda times of del g upon del x, so this quantity, and 4 is equated to 2 lambda y. Okay, so from this you can write your x value as 3 upon 2 lambda and y value as 4 upon 2 lambda. If you give this one into g of I, if you substitute this one into g of I, it is going to be 9 upon 4 lambda square plus 16 upon 4 lambda square equals 1. Therefore 25 equals 4 lambda square, and this is very well tells you that your lambda square is 25 upon 4. Therefore your lambda is plus or minus 5 upon 2. So you get your lambda value. So if you give this lambda value into your x and y, that is gonna be your x is what? 3 upon 2 times of plus or minus 5 upon 2. So this 2 and 2 gets cancelled. So you are gonna have plus or minus 3 upon 5. And y is 2 upon plus or minus 5 upon 2. So that is going to be plus or minus 4 upon 5. So you get your x and y values. Now if you substitute your x and y values into 3x plus 4y and see what is happening, you can very well see plus 5 is the maximum value and minus 5 is the minimum value. Okay. And if you have two constraints, what should be done? Instead of equating your del f to lambda times of del g, you will have, you take the first function as g1 and the second function as g2. This is del g1 plus mu times of del g2, and you will have these two constraint equations. Now with the help of all these things, you will have to find out the values of x, y, z, lambda and mu. Okay, here you have a plane that cuts the cylinder x squared plus y squared is equal to 1 in an ellipse. So that is, you have a cylinder and a plane which is cutting. The intersection of these two things gives you a ellipse. Okay, now you will have to find the points on the ellipse. Points on the ellipse that lie closest to and farthest from the origin. That is, you will have to find out the closest distance. The closest distance is given by some point, so you'll have to identify that point as well as the longest farthest distance from the origin. So for which we consider the function is the distance formula, and you have these two things. And from this, if you find your del f, it is going to be 2x, 2y and 2z, and from here your del g is 2x, 2y and 0. Your del g2's del g2 is 1 comma 1 comma 1. So if you give these values into this and equate them, that is, if you just equate the I coordinates, y coordinates and k coordinates respectively, this is what you are gonna get. Okay, and the value of mu shall be replaced with a 2z, and that is why your first two equations becomes 2x is equal to 2 lambda x plus 2z, 2y is equal to 2 lambda y plus 2z. So from which you can calculate these things. Okay, these are satisfied either if lambda is 1 and your z can be 0. If your lambda is 1, then this forces that your z is 0. Okay, if lambda is not 1, then your x can be written as z upon 1 minus lambda, that is same as that of y value. Okay, these two are the possibilities. If z is 0, then if you solve for equations 3 and 4, you get x squared plus y squared is 1, and your x plus y is also 1. Okay, so you will have to solve this simultaneously. So how to do so? So what shall we do for this? So what we have assumed is that z is 0, and if we have to solve, so the squaring of these two values has to be 1 as well as the sum of these two values has to be 1. This forces either x has to be equal to 1 or y has to be equal to 1. So if x is 1, you are going to get 1 0 0. If y is 1, you will get 0 1 0. So these two are the possibilities. Okay, so that you can see 1 0 0 and 0 1 0. These two are the possibilities. If x and y are same, that is, we are coming to the second case. So if it is so, then we would get you can substitute x is equal to y into this, and you see your x value is coming out to be plus or minus under root 2 upon 2. Okay, and here you get z is equal to 1 plus or minus. So when we have plus here, we have minus here. That's sort of a thing we have here. Okay, so 2x squared is equal to 1 and x squared is 1 upon 2. Therefore, your x must be plus or minus 1 upon under root 2. So just to make this quantity as the integer value, we just multiply and divide by under root 2 and we change this to. So here you can see these things happening. Okay, if you have plus here, you will have minus here. If you have minus in x, then you will have plus in z. So this contributes your points. Now we will have to substitute all these 4 points into the function f of x, y, z, that is x squared plus y squared plus z squared, and see which is the minimum and which is the maximum. Among these 4 points, there are 2 points which is closest to the origin and the other points are farthest from the origin. Okay, thank you.